So let's come back to the third important concept that we want to cover in this lecture, which is the concept of determinant. Okay. So what does determinant mean geometrically, and what is the utility of determinant and what it does, right? One way to think about determinant is it actually is a function that extends or shrinks different transformation, or it extends and shrinks different objects which are captured through transformations. So let's try to get some meaning of this. So let's say before transformation you have some object, right, and maybe we can take and discretize and get vectors that represent this boundary, right, and if we perform some transformation on it, right, it might expand and become bigger. Okay, the initial vectors which are shown in yellow and red, it becomes bigger, and correspondingly by applying the same thing on the discrete points on the initial object, that object might become bigger. What matrix must, essentially what a matrix measures is the factor by which the area of this object is increasing or decreasing. So this factor by which the area of that object grew is essentially a geometric way to understand what determinant does. It basically measures that increase or decrease of the area of an object, which could be achieved through different transformations. Okay. So let's try to conceptualize some of the concepts. For example, let's say we have this grid, right? And in this grid we have simple initial grid where I and j is there, and what do? We have one unit of area defined in this grid. Okay. Now when we take a matrix, okay, and we calculate and we do the transformation of this matrix, and this is some example that we are following. So now in this is the transformation that we have done to the unit vectors I and the unit vector j in the previous grid by applying this transformation. So one of the things that we can do is we can take a determinant of this matrix and we can compute the value of that determinant as 0 times minus 1 minus 2, 2, and this will come out to be a value of 4. So now if you take the grid that we have arrived after transforming the initial unit vectors I and j, then you will see the area that of the unit cube of the new grid that is there, that is going to be 4 times the unit area that was there in the initial grid. So let me quickly go back to the initial unit grid so that you can understand. This was the 1 unit area. Okay. Now if we transformed it and we got a new grid, in the new grid the unit area of the grid itself became 4 times, and that is 4 times the original unit area. And why? And how do we measure that? Essentially, if you take the determinant and compute this value, this is going to give you the measure of how an area is shrinking or increasing with the application of a determinant. And that's the geometric intuition, or that's the geometric way of understanding what determinant encapsulate. It essentially encapsulate the factor by which things are moving, things are extending or decreasing when a linear transformation or a matrix transformation is applied to a given vector. Okay. So again, let's take and this is to what happens to a small grid. A square grid must happen to all the other square grid too. And what I mean by that, if you have this different types of squares which are in the original gridding system, and if you do transformation, right, the new transformation, their area will increase by 4 times. So this is going to be constant if you apply a similar gridding. Okay. So now one more aspect of the determinant is the output of the determinant calculation could be positive or negative. So when we are doing this computation, in this case it came out to be positive, and in some case this determinant value is going to come out to be -4, -5, and so on. So it could be positive or negative. So what is the meaning of a positive determinant and a negative determinant, right? So let's try to understand, and it is essentially with respect to denoting when the determinant, what are the direction of the area computation that we are having. So this has to do with essentially right hand coordinate system, where you have, let's say, index finger, right, representing I, and the middle finger that is representing J, and if the thumb is pointing out, right, you have a determinant that is positive, and that's the direction of the determinant. If you have a thumb which is in which you have which is thumb is facing down, which means that J is right of I, then you essentially have a negative direction and negative determinant. And that's, so the sign is corresponding to the area corresponding to the direction and the orientation of the area, and that's the geometric meaning of, sign in the determinant setting that we have, right? So again, all the concepts that we have discussed today, which is linear transformation, matrix multiplication, and the determinants, are also applicable for 3 or more dimensional scenario, and you can extend some of these ideas to those different scenarios, and for that you can find out, different formulas. For example, if I take, this determinant, which is in the 3D, then I have a numerical way of computing the determinant value. Okay, so in the previous example, we showed you how to do the determinant calculation for a 2-dimensional matrix. Here 2 by 2 matrix, here we are doing it for 3 by 3 matrix, and essentially you can break this down into simpler computations. So you can take this, and A is multiplied by EF and HI, and you can break it down into these computations, and then you can simplify this, and finally you will get this equation, and once you compute, it will output you a single value. And what that value is, again in 3D, it will be extension or decrease in the volume of the object that is embedded inside a 3D space. So it moves the concept away from area, it moves to the concept of volume, which is embedded in 3-dimensional space. Okay. Now, one more important thing that I want to discuss before I finish this lecture, which is what happens if you are getting a 0 determinant, and what does it mean geometrically? Let's think about it for a few seconds before answering this. So, whenever you have a determinant that is 0, one of the following cases are going to happen. So, remember our unit vectors that we are talking. So, the unit vector I and j that were getting transformed, you might have some transformation. For example, you might have a transformation which is not changing I. So, you might have 0, 0, okay, and then you might have a transformation which is taking j, which would be, so 0, 0 I, and some transformation which is taking j and it's making it overlap 2 I. So, it could be -1, 0, j. So, if I use this matrix which is 0, 0, -1, 0, and apply this transformation to unit vectors, what is going to happen? This is going to transform this unit vectors that we have. What this transformation will look like? So, the transformation will look something like this. Let me try to explain. So, the I is not going to move, it is going to remain because this has not transformed. But the j is going to rotate by clockwise and 90 degree, and it's going to align in the same direction as j. So, both the unit vectors in the transformed space are essentially in the same direction, and if that happens, then you will arrive at this case where you have a 0 determinant. There might be another case which is possible, in which case, right, you might have essentially I in this direction, and then j is in exactly 180 degrees opposite to it, and in that case also you will fall into the same situation. Then you might have a 0 determinant. So, 0 determinant means that the unit axis that were initially there when transformed essentially are in the same direction or exactly opposite direction, right? And so there is no way for you to have a area in this new transformed grid, because how do you do gridding here? There is no way to do for you to be doing gridding here where an object could have any area. So everything will shrink down, and any object in this transformed unit vector space will essentially have a 0 area, and that's why is represented by a 0 determinant. So this is a way to understand what happens when your determinant gives you a 0 value. Okay, so with that we'll stop, and hopefully you got some useful insight about and the geometrical intuition about what is linear transformation, what are the meaning of matrix multiplication, and what does determinant encapsulate. Summarizing, linear transformation is essentially numerically is an operation that is associated with multiplying a vector with a matrix, and it basically transforms a given input vector and moves it to a different location. Whereas matrix to matrix multiplication is essentially composition of different transforms for transformation, and you can use the unit transformation to do very interesting things. Whereas the determinant is the measure of how things are extending or contracting in the overall gridded space when you are doing matrix multiplication, and that's the different meaning. With that, we'll stop and we will come with next lecture where we will discuss some more concepts related to vector and matrices.